Okay, so just a reminder that the syllabus for the course is here, as I always say, and then we have a document here that is where you can type notes, anything you feel like typing. Many good things that could go in there. One is if people want to take notes, it's totally cool. Sarab has been a bit of a scribe. But another thing is if you have a question or something, or you think I've said something wrong and you're too shy to just shout it at me, which means you're being too shy, you can still type it in there and I will answer it. I do look at those notes. Good. Today is model selection day. And I wanted to say I have kind of 6 things I want to say. So let's start. The first thing I want to say is about absolute model testing. So when I was a kid, people don't do this so much, but when I was a kid, if you did some data analysis, people would ask you about the chi-squared of your model. And people don't do that so much, partly because the community's gotten more sophisticated. But I just wanted to say that there's this concept of absolute model testing, meaning is your model a good model, versus relative model testing. And the first thing I want to say is there's no such thing as absolute model testing. It just is not a thing. So people used to do this thing that you would say the absolute model testing thing when I was a kid was that chi-squared should be roughly, I guess I should do like this, the number of degrees of freedom in your model. Does that ring a bell? Plus or minus, if you really went to town, the square root of 2 times the number of degrees of freedom. I think that's correct. Anyway, it's something like that. This is your expectation for chi-squared. And so people would, compute their model, check chi-squared, and if it was much bigger than this, they would say, well, the model is bad. And then people would say, oh, that paper was interesting, but chi-squared was very large, so that model must be wrong. And those statements are just totally incorrect. This is only true in extremely special circumstances. The special circumstances include, among the following, all your noise is Gaussian and you know all the Gaussian noise variances correctly, which has never been true in the history of human thought. Second thing is, the number of degrees of freedom is actually impossible to calculate in general in a model, because it's not just the number of data minus the number of parameters. In a linear model, it would be the number of data minus the number of parameters, but in a nonlinear model, there's no well-defined definition of this object. So it's both impossible and wrong, and it doesn't really test your model so much as your noise model. And your noise model isn't usually one of your fundamental assumptions. Your fundamental assumptions are like lambda CDM explains the CL. Like for instance, WMAP, on this basis, WMAP rules out lambda CDM. Because chi-squared was outside of this range. When in fact, WMAP is an amazing confirmation of lambda CDM. It beautifully explains the CMB data. So this is just totally wrong. There's no such thing as absolute model testing. We're just going to forget about it. We're not going to look back. I would say one more thing, though, is that statisticians have often said to me, chi-squared measures the size of your data. And the reason they say that is once you get enough data, you will always violate this. Like maybe if you have like 5 data points, chi-squared is of order 5 and you're cool. But once you have 500,000 data points, the tiniest wrongness you have in your noise model or your model will make this blow up to something big. So once data sets are large, you will always violate this consideration. You'll always have chi-squared larger. And it's not a problem. It just says you've got a lot of data. So luckily, that's kind of over these days. People don't make these arguments in physics so much anymore. But whenever you see that argument, you should push strongly against it, because I've seen seminars in which a graduate student presented a model and some senior person was like, well, your model's obviously wrong because chi-squared is larger than the number of degrees of freedom. And like, that is not true. That is just absolutely wrong. And so,
it's because the sigmas that people use aren't representative.
Yeah, I mean,
in
principle,
if you really understood what was the source of the variance, it
Good.
should still work.
No, Glennis says, in principle, this is correct, and it is, and it is true. Like, this is literally a mathematical result. It is the chi-square distribution.
If it's Gaussian and you know the
Right.
variance.
And so if you have a situation where you really do know the variances, or you can learn the variances or something, then this starts to become an interesting question. And in fact, there are cases where your noise is very close to Gaussian, and you could build a model for your variances, and then you could use this like the consideration that your answer should fit the chi-square distribution. So then this would become like the likelihood in some sense for your noise model. So I think of this much more as like, exactly, I'm gonna agree with that completely. I think of this as much more as like a likelihood for your noise model than a question of whether your model is good.
Are these assumptions true in particle physics?
In
They
particle
can be.
physics, exceptionally, because there you usually can tell, there it's usually a measurement uncertainty. But in astrophysics, it's almost always somehow astrophysical noise that's making the variance, and the measurement uncertainties are in many cases really small. But if the measurement uncertainties dominate, then it can be good.
Exactly. So there's I'm just for the audio, I'm saying there was a conversation about when is this true in particle physics or astrophysics. You can only even hope to be writing an equation like this if you have a really solid noise model. And there are some places where we have really solid noise models. So for instance, in like CMB bolometry, like you have bolometers that have a thermal noise, and you are observing a thermal spectrum, and the model is like linear growth from CDN. Like there are some places where this could actually be true, but in most things that most astronomers do, we don't have control over all of our noise sources. And Glennis actually just mentioned that there's also a kind of noise that comes from model wrongness or systematic uncertainties or calibration issues or whatever. And that definitely won't fit into whatever calculation you've done here. It could in principle, but it won't. Now, we will come back to some of the things about like Gaussian noise and stuff when we do Gaussian processes in a few weeks. So when we do Gaussian processes in a few weeks, we'll talk about noise models and learning noise models and things like that. So that some of that will come back. But I just want to make very strongly, the first of my 6 points is very strong point that we should forget about absolute model testing. We're only going to think about relative model testing. And this kind of reveals a little bit my Bayesianness, because for Bayesians, you can only ever compare models, whereas frequentists are in principle able to make an absolute statement about a model. But as I'm saying, I think the absolute statements about models are almost always wrong, because the model includes all sorts of noise and calibration things you don't care about. Yeah, Vivian.
So let's say, okay, I believe you, but I want to, also go and check my sources and say, why should I push back to this? So I was saying that in the mathematical derivation of this, there is somewhere of an assumption that the noise model is perfectly known or the noise model is Gaussian. And do you have in mind like how, like a reference for that?
Good. I don't have the question is like, what are the assumptions underlying this? I can say them heuristically. I don't have the mathematical, but if you follow down chi-square distribution on Wikipedia, it should be a pretty good. In fact, Wikipedia is pretty good on all probability distributions, and this is a property of the chi-square distribution with new degrees of freedom. And it is this, your residuals will exactly obey this when your noise is exactly Gaussian.
Okay.
You know the noise variances. Okay. Your model is a linear combination of k components, and k is less than the number of data points you have. And your data were actually generated by something in the space of that model. So it's like, it's a ferocious set of assumptions. But under those assumptions, you can simulate, and you get this beautiful chi-square distribution. It works beautifully. And the chi-square distribution is very, very nice thing. And it's in the exponential family, so it has a lot of nice properties.
In case you didn't reemphasize it, you have to simply know the value of sigma for every data point to calculate it.
Good. Glennis is just emphasizing that to compute this, you need to know the error variance of every data point, and they're all in principle different. And of course, and that's where, and remember, we started in the first couple of lectures in this series, reminding ourselves that chi-squared is data minus model, transpose C inverse data minus model. That's the definition of chi-squared, although usually it's written as a sum over data points of residuals over errors squared. But But this is the chi-squared that is distributed like that. Yeah?
Okay, so when it comes out that this is not the case in your model, then you say, okay, one of those assumptions must be violated. And what people often say is, there's some additional error term.
Yeah.
And I will either scale up the errors of all my data points by the square root of chi-squared, or I will add a constant error to all my data points, or fractional error, or intrinsic scatter.
Yeah.
So, what is the approach that one should use with them?
Good. Saurabh is asking the question, which is when you do find that this is violated, what do you learn? Do you learn that you need to add additional scatter to your noise estimates? Do you need to scale up your noise estimates? Do you have to fix your model in certain ways? I think we should talk about that in a later session of this class. The thing about data analysis is you do an experiment, you make some measurement, you see problems with your model, and you upgrade your model and you do it all again. And there's this kind of iterative process by which we do data analysis. And my view is that the way to see that there's problems with your model, it's sure, if you get chi-squared very large, clearly there's a problem with your model. But the way to look at that is not just to look at chi-squared, it's to then visualize your model in the space of the data and ask, what part of the data is it getting wrong? And then that usually shows your model's just above all the data points, or below, or your model has curvature and your data don't, or vice versa. And so my view is that the way you figure that, this might be a clue, this being large might be a clue that there's something you need to track down. But the way you're going to track it down is by visualizing the model and the data and the residuals in relevant frames or with respect to relevant things. That's how you're going to learn, and that's how you're going to upgrade your model. And then notice you could have done that without looking at chi-squared. You should basically just visualize the heck out of your model, your data, the residuals in all the different directions you want to look at. I think that's really my advice. And maybe we should have a class later about model elaboration or model building, which I think it's an interesting set of issues. Good. Okay, good. That was point 1. Let's get to point 2 in my notes. Point 2 in my notes. Model selection is a decision. This point is either obvious or bizarre, but, and I don't know which, but we tend to think, oh, I have a set of models, I have to figure out which model is correct. I'm finding the correct model. But my view is that there's no real sense in which one model is correct and another model is incorrect. It's more that different models have different use values. Some model can deal with certain kinds of data, another model can deal with other kinds of data, one model can deal with all the data but less well, and every investigator has different needs for their model and different goals for their model, and models are like tools that you use for doing something, making a measurement. Why are you using Lambda CDM? We're using it as a tool to measure cosmological parameters or understand the age of the universe or look at the initial conditions or whatever. It's a tool for doing some other thing. So once you realize that model selection is a decision, then you start to realize that a lot of other things come into play other than correctness. Correctness of the model is only part of your decision making. So correctness is involved, but there's also some kind of utility involved. And I really mean utility in the economic sense, people need to make decisions for reasons. So one example I like to give in this context is when people simulate the solar system. If you want to make the solar system ephemeris, you could do model selection. You could treat the solar system as purely Newtonian. You could treat the solar system as Newtonian with first order post-Newtonian corrections. Or you could treat the solar system with full general relativity. Which is the correct model? Obviously the correct model is full general relativity. In fact, even that's probably only an approximation to the truly correct model, which is quantum gravity. But anyway, in general relativity is clearly more correct than Newtonian plus first order corrections. And yet, we simulate the solar system using Newtonian plus first order corrections. Because we want to be able to simulate the solar system for more than 5 minutes. with all the compute hardware on Earth. I don't know, actually I was trying to figure out on the way to class this morning whether I could compute how much compute time it would take to compute the solar system in full GR, but I bet you can only do a few minutes of the solar system in full GR. And so that shows you that the choice of what model you're going to adopt or use or what's your model involves utility. You might want your model to be computable. You might want your model to be interesting. You might want your model to be predictive. You might want lots of other things about your model other than just whether it explains the data. And to think only in terms of whether your model explains the data is making a mistake. Now, if you go down this path, which I'm only going to touch on, I'm not going to go down this path fully. Going down this path, several crazy things happen. One crazy thing that happens is you confront Bayesian decision theory. And my personal favorite reference for this is the Jaynes book, chapter 13. So there's a book by Jaynes called like Probability Theory. It's called Probability, the Language of Science, or something like that. Anyway, it's the big book by Jaynes on Bayesian. Jaynes is like absolutely like, I don't even know how to say it. Like Jaynes this is the Bible of Bayesianism, this book. Chapter 13 is about decision theory, and it's hilarious and interesting and insightful. It's great. So Bayesian decision theory takes all the model selection choices you have and makes them impossible to do. For two reasons. One is Bayesian decision theory involves unbelievably challenging integrals that you have to do. So that's one problem. And another problem is that Bayesian decision theory involves specifying your utility in a way that you can do integrals over it. And most of you don't even know what your utility is. And I can go even further on that. No one of you can know what your utility is because your utility is supposed to be your long-term future discounted free cash flow. That's your utility, whether you know it or not, it is your utility, but you can't compute it. That's what the words long-term mean in economics. I don't know if you've ever read any microeconomics, long-term means you can't compute it. But anyway, for all sorts of reasons, really taking model selection to be a true decision and actually executing it as a quantitative decision-making thing is crazy and impossible. So don't do that. And then I'm going to criticize the standard thing Bayesians do. By the way, Bayesians should be making their decisions this way. If you think you're a true Bayesian and you've written your papers where you've done Bayesian evidence calculations and they're horrendous, you should have done Bayesian decision theory calculations because actually it's more principled to do Bayesian decision theory than to do Bayesian evidence. And Bayesian evidence is just as hard as this and less principled. So anytime you've ever computed a Bayesian evidence, you've kind of made a mistake because you should have done this. And if you did, and this is impossible, just like Bayesian evidence is impossible, which I'll talk about in a second. We'll get there in a second. Anyway, that's just the stub. I'm not going to go really much further on utility, except I am later in the class going to propose a utility that we could adopt as a placeholder for our true utility. Our true utility is impossible to write down, but there are placeholders that we might be able to write down. One last thing I should say is I believe there is exactly one paper in the astronomical literature that uses Bayesian decision theory to do anything, and it is astrometry.net. This is the system we built that recognizes images on the sky, and because we knew that we would destroy our reputations if we told people what their image was and we were wrong, we knew that to give wrong answers to people would be very damaging to our reputations. And because we were thinking about it reputationally, we realized we had to write it in terms of utility. And so we charge ourselves a certain amount of money for being wrong, and we give ourselves a certain amount of money for being right. And then we could build a utility matrix, and then we could decide whether or not to give people answers. So if you put an image into astrometry.net and it doesn't recognize it, it doesn't mean we don't know what the right answer is. It means that we don't know it with enough confidence for us to be willing to place the bet. It's based sort of on an odds way. So this paper is amazingly long, but if you dig down, you'll find there's a section about decision theory in there. And I think it's the only place it's really been used in astronomy. And I don't recommend doing it yourself. Don't try that at home. Okay, good. Good. So now let's go. Now there's, if we go now to think about model selection in the more, those are crazy comments. Let's start to get practical. This is supposed to be a class of practical data analysis. So let's get practical. So the first thing I want to say on the practical side is there's two kinds of approaches to comparing models. So we're in point 3. The two approaches are more or less likelihood methods, so more or less methods where you're asking under which model is my data more probable? Are my data more probable? Anyway, Mike Blanton thinks that data is like grass.
It's been officially declared to be singular now.
Oh, really?
The Oxford Dictionary.
Hey.
Oxford went
It's a
singular?
big win. It's a big win. We can all celebrate.
Brutal. All my papers are now wrong. I've been a plural pedant for years. But anyway, Mike Blanton.
You have good company. Yeah.
Mike Blanton found a compromise position, by the way, which is that if you think of data as like grass, like a mass noun, then you use singular pronouns even though it's a plural object, or hair. Right? You don't talk about your hairs. You talk about your hair, even though there's a lot of them. Anyway.
Does it matter at all? That's my main question.
Wait, are you saying it doesn't matter what
Or is?
It matters a lot.
Okay, you're all the class doesn't matter. If that doesn't matter, I don't know what matters. Good. So there's kind of methods that are asking the question, how likely are your data? And Bayesian decision theory falls into that class. How likely are your data? And there's another set of methods which are kind of, does your model make good predictions for new data? Does it have predictive value? And that's a different class. Although these two classes overlap a lot, and the Bayesians would tell you that the Bayesian evidence is telling you about the predictive value of your theory. And I'm about to argue against that, but the distinction is not completely clean here. But I'm going to make this distinction that there's kind of likelihood-based methods and there's prediction-based methods. That's going to be a distinction I'm going to make, which is a rough distinction. So let's start with the likelihood-based. And the simplest likelihood-based way to choose between two models is so let's do a little terminology. So let's imagine I have a likelihood function which tells me the probability of my data, and I'll assume the data is some big collection of data. This is the LHC data. This is like the Atlas data at LHC. And then there's a model, well, let's call it, so this model has some parameters. There's going to be some parameters in model A. And then there's going to be some deep assumptions of model A. So I'm using this as a placeholder, this H, to be like a placeholder to say there's all these assumptions. So let's say this is the model that there's a standard model, the standard model that includes 125 GeV Higgs particle. So this is one of the models I'm considering. And then there's another model I'm considering where I can write down again the probability of the data given some set of parameters now in a new model. And that new model is, say, the standard model with no Higgs in it, which of course wouldn't be the standard model. No Higgs in the band or whatever. So, and now you can ask, have we discovered the Higgs? And more or less, this is a little bit extreme, but more or less, the way the Higgs discovery, I'm being very, very cartoonish here, but more or less, the Higgs discovery was that the optimum of this function, optimizing over these parameters, was larger than the optimum of this function, optimizing over parameters, by a certain factor, which corresponds to 5 sigma.
But that's a chi-squared method, right? Essentially.
But it's not absolute, it's relative.
No, yeah.
Good, the question is, isn't that just chi-squared? Yes, it is just chi-squared, but instead of asking absolute questions about chi-squared, we're gonna ask differential questions. Because we're gonna ratio these probabilities, and of course we're gonna take the log, and the log of the ratio of these probabilities is gonna be the difference of chi-squareds, right? More or less. If you have the same data in here, it will literally be the difference of chi-squareds if the model's Gaussian or whatever. Which of course in the LHC model it's not Gaussian and all that stuff, so I'm being very cartoonish. But more or less we're talking about the differences in the logs of these two probabilities. And that is and at some level, the Higgs discovery was that that difference got larger than what's called 5 sigma. So just sidebar, I believe that the Higgs discovery is that the ln of probability this, given theta A, HA, minus the ln of the probability of y given theta B, HB, and here I'm going to put little hats on these to remind ourselves that they optimize these parameters. They got the best values they could get for these parameters. They're like the maximum likely parameters, the maximum likelihood parameters in each case, and that should be setting off a little alarm in your head, because of course the different models will have different numbers of parameters. One has a Higgs mass and one doesn't. One has Higgs couplings and one doesn't, and so on. So there are different parameters in the two cases. So that should be setting off a little, and we're going to talk about it in just a second. But more or less, Higgs discovery is that this was greater than 12.5.
There's a way to do it where you, I mean, this issue,
Yeah.
I was going to argue with it. That's the reason I'm coming to these talks. I'm hoping you'll have something.
Yeah, good.
Not just this.
Good. Good. Glennis is about to, but just for the mic, Janice is about to tell us why she's here.
Besides the fact that I love hearing it. Well, I think that there's a really deep problem, in my opinion, is how do you compare models that have different numbers of parameters?
Qualitatively different models or models that have different numbers of parameters. We are about to discuss that.
But in many of these applications,
Yeah.
people get around that by just saying, well, what's the, for example, is there a source from ultramarine cosmic rays? Well,
Yes.
you compare the sky map with and without a source, and then you, so there you haven't changed the.
Yeah, right, exactly, yeah.
You can.
Good.
Well, that's actually.
Let's come back. So Glennis is asking about like how you do this with multiple parameters. Let's come back to that a little later, because there's two things that are going to happen. One is we're going to talk about what happens about the fact that the models have different levels of complexity, and then there's going to be another thing I want to bring up at the end, which is what happens if the models are nested. So the model of the standard model without a Higgs and standard model with Higgs are nested models. You've just added something to the model, and that leads to a new simplification that is actually leads to another way of doing model comparison. So there's two things going on. One is different numbers of parameters, and one is models are often nested. And astronomers are often in the nested case because we're asking, is there 3 planets in the system or 4? And the 3-planet model is nested inside the 4-planet model. So if I haven't answered that question by the end, let's bring it back. Why do I say 12.5 here? Why do I say 12.5? It's because 5 sigma would be a chi-squared of 5 squared, and it's half chi-squared. The ln probability is negative a half chi-squared. But I'm just making that up. I don't even know if that's correct, but it's closely correct. Okay, good. So this should just be in a cloud, because this is like what Hogg's thoughts on the way into work was that the Higgs boils down to that, which is pretty funny. Okay, good. Oh, right. So now, if you just do this as actually, Glennis's point is already here, because when I look at my notes, the next point is, so you can think of this as a difference of log probabilities, right? That's how I said it, a difference of log probabilities. And if you're in this Gaussian case, this difference of log probabilities is just 1/2 the difference in chi-squared, actually with a minus sign. So this would just be the difference in chi-squared between the two models. And so if you're working in the Gaussian case and you have chi-squared like this is your likelihood function, or this is your log likelihood function, then of course your log likelihood function is actually minus 1/2 that. Then the difference in log probabilities is just the difference in chi-squared. So it's very beautiful, and it justifies working with chi-squared. And it's also why we do parameter estimation using chi-squared, because when you're finding the best parameter, you're finding the best chi-squared, you're taking differences of chi-squared between different values of your parameter. So you optimize chi-squared because you're trying to find the parameter values such that there are no other parameter values with better chi-squared, because that's a likelihood ratio. You can think of, up till now we've done everything continuous. Our parameters have been continuous. You can think of this model choice as like a discrete parameter, which takes the value A or B, and then you can no longer smoothly optimize. You have to discretely optimize. You have to compute both and compare. And in discrete optimization, that's your only option. The mathematicians will tell you. Your only option is to try all options and then compare. That's the no free lunch theorems if you want to search, web search something. Okay, good. Where were we? There was something I was going to say. Oh yeah. So of course, as Glennis pointed out, and in general, you're looking at this and you're a little suspicious about this because it involved optimizing these parameters. You somehow want to penalize the model that had more free parameters, because if it had more free parameters, it probably has more freedom to fit the data. Now, the difference between parameters being linear and nonlinear is a big deal, and I could go on forever. I have an adversarial example. I have an adversarial example that has 3 free parameters that can fit any one-dimensional data set of any size, no matter what. And if you want to see that, I will talk about it later. That just shows you that number of parameters isn't a thing. But in linear models, it's a thing. And as you add more and more linear components to a linear model, it's true, you get more and more freedom to fit the data. And so we should penalize for the number of parameters. Yes?
When you say linear model, you mean that the model is linear in the parameters?
The model is linear in the parameters. We defined linear model in an early, but thank you for that.
Sorry,
Yeah, let me just,
okay,
no, I think it's a good thing to just re-mention here, because a linear model is that this model expectation is a sum of coefficients times, like if this model is, say, a function of x, there's some basis functions, g of x, that get multiplied by parameters, and these are your parameters. Your only parameters are prefactors in a linear sum of functions. That's a pretty general thing. You can do lots of things there. These can be sines and cosines and spherical harmonics and whatever you want. They can be complex functions. But if they sum, and the only parameters you care about are the amplitudes with which they coadd, that's a linear model. That's when the chi-squared theorems become correct. And that's when you can correct this likelihood ratio for the number of parameters.
And you can also do analytic marginalization, right?
Yeah, well, it depends. No, only if you have a prior.
Okay.
Right? And in fact, I'm being very careful in this class to be frequent is safe as much as I can. There will be moments where everything I've said so far is frequent is safe. But at some point you might have to do an integral, and then we'll have to become Bayesians. We will have to do an integral in a minute. You have to do an integral to do you have to do integrals to do this utility maximization, and that's why Bayesian decision theory is really the only consistent decision theory. Of course, there are people who would choke to hear me say that, because there is a whole frequentist decision theory thing about min-max, like minimizing maximum loss or maximizing minimum, I don't know. There's some complex objectives people come at that don't require that you do integrals. But the only thing that seems consistent to me is to do integrals. Certainly if you want to place bets on the horses with model selection, you want to do integrals. By the way, Kentucky Derby happens during this class, so maybe we should do on the Friday before Kentucky Derby, do a handicapping session, because that's really applied statistics. Okay, good. Little concerned. Okay, now there are a set of corrections. There are a set of methods that take these likelihood ratios and correct them based on different numbers of parameters. And they're all called information criteria. There's the AIC, and there's the BIC, and there's a set of other ones. And they all basically are of the form that you take this delta chi-squared and you add to it. So this is, remember, this is negative delta chi-squared. You prefer the model with lower chi-squared. So higher likelihood is lower chi-squared, right? So what you do is you take the models, you compute delta chi-squared at best fit, and then you add a correction which is Q times the number of parameters, where this Q is some constant and it's different for the different information criteria. Like for one of them it is a half or 2, and for another one it's the log of the number of data points you have. Strange thing. Anyway, I don't really care, because these methods are really, basically, if it matters what number you put here, you're probably living your life wrong. And you basically are going to have to say these models both fit the data reasonably well. If it matters what number you put there, like if you put a bigger number there and one model is preferred and a smaller number and the other one's preferred, that means that you basically can't decide between your two models. They're both equally good.
You mean, so this is exactly the thing I wanted to ask
Yeah.
about. What I wanted to understand whether in the world of statistics and thinking about probabilities and inferences, people had arrived at a principled way to address this, because everything I know is pretty ad hoc. I mean,
Good.
it's, something is reasonable, you think about entropy, and so on, but ultimately it seems ad hoc to me.
It is ad hoc. Glennis is asking how ad hoc is this? I would say it's pretty ad hoc. I'm going to give you two methods that I consider to be principled.
Okay.
One of the methods is going to be, one of the methods is going to be prediction based on how well your model predicts new data, and I think it's extremely principled and it's extremely hard to argue with. It's a beautiful thing, so I'm going to show that. We're nearly there. The other, on this likelihood side, there's two kind of principled things to do. If you're truly Bayesian, and I mean a subjective Bayesian, so you've created your priors based on a true analysis of your beliefs, which would be very hard to have, but if you did, then the Bayesian evidence does tell you which model is more in line with your beliefs and the data, more in line with the intersection of your beliefs and the data. And that's principled, it's correct. But you'd have to be a perfect subjective Bayesian, and I have not met one yet.
Not one with tenure in physics.
In fact, I'm as close to a subjective Bayesian as you can find in astronomy, and I can't do it. I can't write down my beliefs as probability distributions. Like, what are my beliefs about variability of the Kepler spacecraft's pointing? I'd have to be able to write that down as a probability distribution over Kepler spacecraft pointing errors to be a true subjective Bayesian. But if you are a true subjective Bayesian, there'll be a Bayes integral you can do that is principled, and even better, you could then write down your likelihood, your utility, and you could actually do full decision theory. But you'd have to be a perfect subjective Bayesian to pull it off. So the only principled things are predictive methods or full subjective Bayesianism. And I just think that is impossible. That's why I'm going to argue, I said in the summary of the class, I'm going to argue that you should use predictive methods. Because I think they're the only principled thing you actually can do. Okay, good. Good. Now it's time for me to explicitly criticize the Bayesian evidence. Okay, so if you're a true Bayesian, you don't like any of this, for several reasons. One is, this involved an optimization. And in Bayesianism, you should be integrating over your parameters, not optimizing your parameters. You should consider all the possible worlds and weight them by their relative likelihoods. So we shouldn't be optimizing, we should be integrating. So the relevant thing in Bayes, so this is point 4. This is what's called, in the literature, it's called Bayesian evidence, which is annoying. I call it the fully marginalized likelihood, which comes to an acronym which has another meaning on the internet, which is good because it's appropriate. So for fully marginalized likelihood. The idea is you don't want to ask what's the difference between the optimized likelihoods. You want to ask what's the difference between the likelihood, the marginalized likelihood, the mean likelihood weighted by the likelihood, or weighted by the prior. The mean likelihood weighted by the prior, meaning how well did your prior beliefs in this model predict the data versus how well did your prior beliefs in this model predict the data. It's about the predictive power of your prior beliefs. And Bayes prefers the model that predicts where you predicted the data better. So you can see how this is getting close to predictive. It's not going to be exactly predictive because we're always going to work with the data we already have, but it's very close. So you can see we're on a path where we're going from likelihoods to predictions. So what does this look like? You compute something which I will call like PA, which is the integral of P of y given theta A HA over the prior on theta A given HA. So this is model A prior, and this is model A likelihood function, and you integrate d theta A over the whole domain of theta A. And this integral, by the way, I have a little note on the internet, on archive, called probability calculus for inference. That's by me. And it's just a little note that just shows you how to construct probability expressions. Like, I can write down this probability expression very easily because I'm just used to manipulating probability expressions. If it's like, why did he write that down? That's basically the only thing you could write down, and this note tells you why, and it does a kind of dimensional, it takes a dimensional approach like units or whatever. So this is like probability for data given parameters, this is probability of parameters, and when I multiply these two things together, this is the joint probability of the data and the parameters, and then I'm going to integrate out the parameters, so then it's going to just become the probability of the data. So when I do this integral, I would get the thing you would call P of y given HA. The parameters have disappeared because we integrated them out. That doesn't mean you don't have beliefs about the parameters. You definitely have beliefs about the parameters. You have both prior beliefs about the parameters and posterior beliefs about the parameters, but you've integrated that all away. This thing is the FML. And the difference of log FMLs is what replaces the difference of chi-squareds in this Bayesian framework. And that is principled if you're a fully subjective Bayesian. And I'm going to say why it matters whether or not you're fully subjective Bayesian in a second. Yeah?
The trouble with this point of view is very much like the trouble with contemporary politics.
Yes, I think I know what you're going to say. Glennis being a particle physicist, we can actually predict a little bit. Yes.
Well, really what we want to know, if we're real scientists, is to try to set aside our prejudices and ask what theory is better describing nature.
Yes, I agree.
And
I agree.
doesn't...
So Glennis is pointing out, why are we computing an integral which is about our beliefs when we should be computing an integral which is about the world? Good. Hold that thought, because you're going to love my recommendations at the end of this. So it's funny because I am close to a subjective Bayesian. I work usually in the Bayesian mode, but I work in different modes depending on what. But when it comes to model choice, I think all the Bayesian approaches are literally wrong-headed. But I have a very simple objection, which it might not seem obvious to you that it maps onto your objection, but it is actually your objection, and I'm just going to say it right now. Imagine I have one of these parameters in here as a true nuisance parameter. It is like the pointing jitter of the Kepler spacecraft. And remember, I have to have a belief about that before I've looked at the Kepler spacecraft. Okay, so before I've looked at the Kepler spacecraft, I have to have a belief about the pointing jitter of the Kepler spacecraft. Okay, fine. I'm a Bayesian, I can take it, I'll do that. So what do? I have some nuisance parameter, which we'll call, theta j. This is the jth parameter. And I have to draw a prior in theta j. And this is some parameter I truly don't care about. So what do? I probably choose a minimum value I could believe and a maximum value I can believe, and I make it flat. Or something like that. I do something sensible like that. Now, somebody else who believes less in the quality of NASA engineers puts their limits here, and their thing looks like this. That's their prior. This is my prior, that's their prior. There's nothing really different about it. We're both making this up. Neither of us have any idea what the Kepler spacecraft's going to do. So we're just making it up. I'm willing to accept this. They're willing to accept this. There's literally no scientific difference between the two of us, except one's a little more skeptical, one's a little less skeptical, whatever. There's really no difference. But notice that now, if graphically I can draw the likelihood in here, of course this is a very high dimensional problem, but let's just think about this one dimension. Now imagine the likelihood looks like this. Notice we get completely different answers for the FML. Because these two priors have to integrate to one. That means my narrower prior is taller. Their wider prior is lower, a Bayesian would say, yeah, of course, you're more right than they are. But I wouldn't say that. I would just say I got lucky. Of course, if it's over here, it would very strongly distinguish the two models, because I would give 0 for that, and they would give a large number. But here, as long as we're making kind of Catholic priors, actually I've used the word Catholic there with the little c, but actually there's a better word, there's the...
Agnostic?
There's agnostic, but there's even better, there's a principle, Cromwell, named after somebody who is important in the history of the church, which is about the fact that all possible things should have some finite probability put on them, which Bayesians should think about more, because I've cut off this little piece here just because I set some flat prior based on some bullshit.
But
so
then you see it and you go back and you adjust the prior.
Yeah, and yeah, good. Wolfgang said, you see this, you adjust your prior, you're well off, that's great. That's exactly what everyone does, and that is completely not allowed. And in fact, there's a bunch of papers that say, like I remember there's a paper on the neutrino hierarchy. So there's the neutrino hierarchy, whether the 3 neutrinos are split in a mass splitting like this or like this. And there's very little data on that, and so your conclusions about which hierarchy is preferred by the data depend strongly on your priors. And there are literally papers in which people like adjust their priors to get the answer they want. I mean, it's just a terrible situation. So, and it's because they're thinking about it in this marginalized likelihood way, which is not the right way to think about it if you really want to ask which is a better fit to reality, which is what Glennis is looking for. So I'm going to propose something which connects to our thinking about correctness, which is to do predictive checks. Use only test models with predictive tests, truly predictive. That's where we're going to go. But anyway, this is a very strong objection to the Bayesian evidence. When I bring up this objection to Bayesians, they say, oh, well, these two differences will only differ by, say, a factor of 3 in this, and we only care about very large differences in Bayesian evidence. Like, one will be e to the minus 180, and one will be e to the minus 189, or 200, or something. So they're looking for very big differences in this log, very big differences in log. But if you're looking for very big differences in the log, this will give you the right answer. You would have gotten the right answer doing that. Any place where you get a clear answer doing the FML, you would have gotten a clear answer doing that. There's yet another issue which I won't go into, but these integrals are generally impossible. You may know that there's a dimensionality, there's a curse of dimensionality. Once your dimensions get towards 10, you cannot do integrals, you cannot do density estimates, you cannot sample posteriors. You can't do anything once you get dimensions around 10. So once you get to models that have more than a few dimensions, so people in the astronomical literature, there's a huge literature about doing this for planet models. Are there 6 planets, 7 planets, 8 planets? Those are models with 40, 50, 60 parameters, and different codes give different answers at many orders of magnitude, because you just cannot do a 50-dimensional integral with a non-trivial likelihood function. It's just literally, physically impossible to do these integrals. So in addition to them being in principle wrong, they're also in practice impossible. Yeah?
Sorry, I'm sorry everybody. I just
Yeah, no,
want to make
Yeah,
sure
no.
I understand this really well.
This is what I want.
Okay.
Yeah.
So your objection there is that you have placed a prior on a parameter, and can you remind me, are you comparing two models there, or are you just sort of like being happy because your likelihood is peaking within the range of your prior?
Good.
Like, I'm not sure of what is good.
Yeah, so Viviana's asking me for a little more explanation of this. So this is just the integral for one model. I've integrated for 2 models and we compare them.
Okay.
Here are the 2 differences I'm giving are all in the same model.
Okay.
So we're in the same model, it's just that I drew this range for a parameter I don't care about, and somebody else drew a different range.
Okay.
And what I'm saying is there's no real scientific difference between the 2 of us,
Okay.
and yet we're going to disagree on what the value of this integral is by a factor of 3.
Because you're saying that that part that depends on the prior is affecting your evidence, so your calculation of the posterior more, well, not more than it should, but significantly.
It actually has nothing to do with the posterior. We would actually, if I drew it like this, let me draw it like this. If I drew it like this, the 2 of us would have exactly the same posterior beliefs about this parameter. There's no difference to our posterior beliefs. We are literally using the same model. The only difference is a slight difference in where we wrote the ends of a stupid flat prior, which we don't really believe.
You marginalize them.
And then we marginalize, we do the integral of the product of these functions.
The problem is, in this instance, the magnitude you assign to FML.
Exactly, the magnitude you assign to FML is different, even though we have the same same likelihood, same fundamental content to our models, and same posterior beliefs about every parameter. We disagree on this integral, which is absurd.
The worry.
Why?
But you have maybe a technical question. Why do they disagree on the integral? The reason they disagree on the integral is this part has to integrate to unity. You see, if I just did this integral, it would have to be unity, right? Because
And
it's.
so that's me. And
So if I broaden
different-
broaden the support of my prior, I drop the amplitude of my prior.
Right.
And the amplitude of the prior is in this integral. So if this investigator has 3 times the support, they have 3 times less the amplitude and they get 3 times less the FML, even though they have identical posterior beliefs about everything.
Well, but your posterior wouldn't that be your posterior like the product of your likelihood times the prior, and the prior is a different level, so wouldn't that also be different? I guess that
Except
why
with the
you-
posterior, you renormalize it so it then reintegrates to unity.
I see, okay.
Good, that's a great question. Yeah. The products, our products are different, but our posteriors are the same because you renormalize to unity.
I see.
This is actually a very good example to think about because it shows where does the prior dependence come in. A lot of people say, well, I'm a Bayesian with flat priors, so that's the same as being a frequentist. It's not quite true. It is true that you have the same beliefs at the end of the day about this parameter, but it's not true that you have the same beliefs at the end of the day about the whole world, like about the relationships, for instance, of different models.
Right.
So,
Even about that parameter, if by chance it had fallen a little bit further out.
Yeah, then there would really be a difference. We'd have different posterior beliefs. Then my model would be bad, and my friend's model
But you
would
wouldn't
be
know,
good.
you might not realize.
You might not realize. Well,
because
especially if you're in
of
high dimensions, you really might not realize. It's hard to even see it if you're in high dimensions. Yeah, Sarab.
I mean, I guess, a frequentist often would say that the whole issue with the posterior is also that the priors matter.
Mm-hmm.
But you're saying this is more subtle, and that the evidence matters much more significantly.
Yeah, the reason this is more subtle because this is a place where your priors matter even if your posteriors are identical. So the posterior in general is much more stable than your any integrals. Which, by the way, is going to come back, if I get to 0.6, which I might not make it, but if I get to 0.6 of my 6 points, we're going to come back to this because in many cases you can turn a model selection into a parameter estimation. And if you can do that, your priors don't matter as much anymore. So, and one thing that's important to remember if you're a Bayesian is if your likelihood looks like this, though you will get different answers for this integral, your priors don't matter at all to your inference of this parameter. You write any prior you like. As long as it has support here, you will have the same, everyone will get the same answer. So in the limit of very good data, your priors don't matter, but they do to this integral. So you've preserved a prior dependence in your problem that you didn't need to have there. That goes away. In very good data, this still cares deeply about your prior. So it doesn't, a lot of Bayesians say, well, once the data are really good, it doesn't matter what your priors are. It does if you're doing model selection or utility calculations. Okay. Questions? Okay, that was a rant. I'm now going to come down off the rant, and now I'm going to say what I think is the right thing to do. Okay, no more ranting. I really have to write that up. I have to write that whole argument up. I intend to, but there's a lot of audiences because I have to write to the statisticians as much as the astronomers. Okay, we're on point 5, I believe. Yes, point 5. I think a very good proxy for our utility is, does this model predict new data? And I think if you think scientifically, how valuable it's been. The physical model that predicts the CMB data with very few additional parameters predicts the large-scale structure growth. And models that predict the spectrum of a star in the optical, just extended into the infrared, predict the spectrum in the infrared with some issues. But we think of when we go to new data and the model still does a good job of new data, we're stoked and we're like, it must be good. And if it does badly, we're like, oh, we must be missing something. So I think predictive power of the model is actually a very good proxy for utility. It's not exactly your utility, because it might be that your most predictive model is one you can't afford to execute, like the GR example I gave earlier, whatever. There are some other things which come in, but a good place to start is prediction. So we want to predict new data, or use predictive methods. And there's two basic approaches. There's many approaches to this. There is a certain sense in which this involves prediction. So I'm going to leave that as an open thread, which we can talk about later. But I think that much more valuable here, so let me write a few words you may have heard before. So one is, in machine learning, when people do machine learning methods, they tend to split their data into train, validate, and test. And if they're very principled, they do this split on the arrival of the data before they start model building. And there's a part of their data that remains the validation set, and then there's part that remains the test set. And more or less the way it works is, as you explore around in model space, you keep checking on the validation data, and when the validation data will prefer some model, and then you do your final assessment on the test. So it's so there's the data that you use to set the parameters of your model. There's data that you use to compare qualitatively different or high-level decision making in your model, and then there's data that are actually used to check your performance. And that's a beautiful split. We almost never do that in astronomy. I have a few papers where we have done this, but it is rare in astronomy. It's not a thing that people do, and it's actually a point where the machine learning people are actually more principled than the astronomers, and something where we could take something on. We like to think of them as unprincipled hacks who just are trying to turn horses into zebras, but in fact, there's some very, very good statistics ideas in machine learning.
Finally, it's widely used in experimental physics.
Yes.
Where like you take
a
year of data and you use a month of it to find out, for example, how the detector is working.
Good.
You practice your analysis, you optimize parameters, and then you apply the analysis line to the rest.
Good. Glennis mentions that in experimental, this is used in a way where you use the first year data, say, to predict what's going to happen for the next few years. And she even used the word blinding. So I was just going to write the word blinding down here. And I shouldn't have, these should be letters, I guess, since what you're doing. Blinding, which is there's a worry in cosmology now that we're working to really precise parameters that we're biasing our results to get the right answer. And you've all seen it happen in your own work. You do an analysis, you get a parameter estimate that you don't really like, and then you go look in the code, and oh, you found that you had a bug here and a bug there, and you fix those bugs, and then it gets better, and then it's still not very good, and you fix some more bugs, and then it hits the value you kind of expected, and then you stop looking at your code to see if it still has bugs. And we've all, we all laugh, but how else would you operate? Are you going to keep checking your code for bugs until you die? Like, at some point you have to publish a paper, so actually you are going to do that, and I think you should do that. I'm pragmatic, do that. But then remember that when the next year's data come in, you're going to check it with the frozen code and analysis you froze after doing all that checking, because then you're actually doing an ab initio test of whether you found all your bugs. And of course you will find that you didn't find all your bugs, and then the only question is whether it mattered. But there's an interesting thing that if you do this blinding, by the way, this is off topic, but if you do the blinding, you must commit to publishing your blind analysis, even if it sucks. In fact, we've been thinking about whether we should get agreements from the journals around that, because the journals don't want to publish wrong analyses, but you have to publish the wrong analysis, because otherwise the blinding doesn't mean anything. So there's a question about whether we should get the journals to pre-agree to publish certain results. And I think it's an interesting question which we as a community should face at some point.
Psychologists do this, by the way.
Yeah.
You can pre-register your hypothesis with them.
Good. Wolfgang brings up the point in psychology, and in psychology these things are being done, and one of the reasons is there's been a replication crisis in the world, and where a lot of famous results particularly in psych, but also in various social sciences, have not been reproducible. And also many drug trials have not been reproducible. And my view is the astronomical literature is also not reproducing, because people will find like galaxies at different redshifts or different sizes or whatever, and they publish that result. And then another survey measures it, and they also find that galaxies are different redshifts or different sizes. So they say, see, we reproduce the result. But then if you overplot the results, they have different slopes. So it didn't reproduce. It's just the opposite. It's not a reproduction of the result. And then, of course, you look in and, well, they measured galaxy sizes differently, and they worked in different band passes, and blah, 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 blah. Fine, but it's not obvious that our results reproduce either. And we tend to go, oh, the psychologists, they have some big problem. Their results don't reproduce. Our results don't reproduce. I mean, the H-naught is different and the two different. So I don't know, but it's an interesting thing to think about, but it does somehow relate to model selection. And actually, one of the big thinkers about that here, I should say, is Stephen Feeney, because he's been thinking about how predictive checks can be used to test models or build models. And Stephen, of course, gave our hierarchical Bayes lecture, and he'll be back again next week. Continue with something, yes?
I just want to say, the thing I wanted to mention in the case of blinding is that it's used, I think, best when it's an opportunity to understand things about the nuisance parameters.
Yes.
That
good.
You can't know in advance, like
Yeah.
Kepler's jitter, or AMS,
good,
the cosmic ray
Yeah.
satellite.
Yeah, good.
It turned out its pointing wasn't very accurate.
Yeah,
stuff
right,
like
good.
that.
Yeah, Glennis is saying a very important thing, which is that this blinding and also what would be called validation in machine learning is very good for dealing with nuisance parameters, like how you deal with your calibration, or how you deal with aspects of your model which are kind of choices. Like for instance, when we extract a spectrum from the spectrograph, you decide, like, do you use a quadratic or a third order or a fourth order polynomial to fit your traces? It's kind of a nuisance, like what are you going to use? And validation is a good way to like click through those choices or make a choice. Because it's a nuisance parameter, you don't really care about it.
But in that context, for example, you might set aside 10% of the Gaia data to tune these things.
Good.
And then use the randomly selected, for example, or a particular region that you were really interested in or whatever. Yeah,
so different people would cut this numerically differently. It of course depends on how much data you have and how valuable they are and how much you care about these things and so on. But that comment very much relates to the C point here, which is cross-validation. And I'm just gonna advertise cross-validation for a minute, because one of the reasons I love cross-validation is not the most statistically safe of these, but it's very easy to do, and it doesn't require that you have made this split before you started. If you didn't do the split before you started, you now aren't firmly in this state, and if you think now, okay, well, Hogg said I should do this split, and you do the split now, it's kind of too late. But it's not too late to do cross-validation, so let me just show you cross-validation. You already can guess exactly what it is if you haven't done it before. By the way, who here has cross-validated before? Good, half the room has cross-validated before, good. So, and it relates very much to jackknife, which we talked about in the empirical error bar stuff we talked about before. Good, we are on target. We are on target. Okay, good. So let me just write down cross-validation, even though I'm... So cross-validation, so if you recall in jackknife, when we did jackknife, we made all the leave one out subsamples. So jackknife, this is like you remembering jackknife. So this should also be in a little bubble, you're remembering this. Jackknife, you made the leave one out subsamples. I'm trying to work all the acronyms I can. And we redid our analysis each time leaving out one data point. Actually, it wasn't necessarily one data point. We left out 1/k of the data. Remember, we had k splits, and for every time we left out 1/k, did the analysis, then put that back in, took a different kth out, did the analysis, put it back in, took a different kth out. And we did that, and we got k measurements, and then the variance of the k measurements was an empirical estimate of our error times a little prefactor, dimensionless prefactor. So same thing here in cross-validation. Cross-validation, you leave out 1/8 of the data, and then you predict it using the model you trained on the leave-out sample. So we're going to leave out 1K of the data. And so we get a training sample. So you have a training sample. So let's call this subsample little k. And so the training sample is all but the k subsample, and the validation sample is k. So there's some actually, by the way, one of the things let me give a piece of advice, a very clear piece of advice here. When you get your data, you have your data you're going to use for your data analysis. The first thing you should do is choose capital, actually you don't even have to choose capital K. You should assign a random number to every data point. You should just augment your data with a random number. And you can either make it a random real from 0 to 1, or you can make it a random integer from 0 to 2 to the n minus 1. But either way, assign a random number to every data point. It will serve you so much use going forward. For one, you can show that if you include that random number in your data analysis, it doesn't improve your predictions. If it does, you have a bug. Another thing you can do is you can cut that random number into k slices, and that makes your k data sets in a reproducible way. So you should literally just add a random number to every data point, put it in the data file, and preserve it with your data. It's part of your data. And then these operations become fully reproducible operations, and you have these tests. In fact, you could even add a whole vector of random numbers if you want. But we just add one. And that's a standard thing we do to our data now whenever we're doing things with the Gaia data. We just add a random number. In fact, Gaia should have done it. Did Gaia do it? I don't think Gaia did put a random number in, did they? Maybe they did. I think maybe Gaia did put it. Is it from 0 to 1?
I don't remember.
Anyway, I think Gaia did. Yeah, I
They
think.
need to be unique with random numbers, or is?
No.
So Gaia has a random.
No, in fact, if you do integers from 0 to 2 to the n, they won't be unique. They don't need to be unique. But that's why a real is better.
Why 2 to the n rather than n?
The only reason that I say 2 to the n is because then you can factor it, so you can then make subsamples that will be roughly equal size by modding that number against 2 to the n. So if you want to do an 8-fold cross-validation or a 16-fold cross-validation, it's trivial to do on those numbers.
Can you just share your seed and then randomly subsample? But maybe I guess that comes down to algorithmic differences in how you do that, right?
Yeah, the question is, could you just share the seed? It's a little dangerous to share the seed just because if there's slight difference in how somebody runs the code or in the generator they have. When they upgrade NumPy, for instance, they don't promise you that the random number generators will remain identical.
But if somebody hasn't assigned them in advance, it's not a crisis. You just
No, you can
assign
just
them
do it
now.
again. Yeah, you can do it now, yeah. And of course, none of this really matters. I'm just saying that it's just good practice to have a random number as one of your data columns because it's a regressor that can't do anything. Yeah, Gabby.
Yeah, but do you say that to reproduce with exactly the same training set? If your model is dependent on the exact training set instead of training.
It's bad, yeah. No. This is not to say that you shouldn't also try other splits. In fact, we learned a lot. In the project that I did with Christina Eilers on mapping the Milky Way, we did an A/B split. We couldn't afford to run our code many times, so we actually did a 2-fold cross-validation. We literally just dropped half the data, trained on this and predicted this, and then we did the other way around. And then we tried different half splits just to check, and sure enough, some of our results did depend on the half split. So it was actually important to do that because then we saw that our half splits were there were some inhomogeneities in the data or something that were causing some additional noise.
So now what figure do you use to test? Like, do you use now chi-squared?
Good. Now let me think, let's be very careful here. So now what I have, so think about these, let's think of each of these k things as a data point. Of course, it's a set of data, right? But this is yk. That's what this validation sample is. And this is yk, And this is yk prime for k, like not include, for k prime not equal to k. Good. It's for all the k primes not equal to k that you assemble all the data. That's this training set. And the validation set is just the data for the kth subsample. So this is my split. And then what I do is I do whatever I do here. If you're a frequentist, you optimize your parameters. If you're a Bayesian, you get your posterior. And then you predict this using that. If you're a frequentist, you predict this at your optimal parameters. If you're a Bayesian, you produce the posterior prediction for this. And the posterior prediction is the prediction at every value of the parameters marginalized with the posterior. So you integrate over the posterior. It's not quite, but it's very related to the evidence. Let's stay frequentist here. I want to stay frequentist for now, but if you write down the Bayesian thing you do here, it looks a lot like this integral. It's just slightly renormalized, so it's less prior dependent. Because what you end up doing in those posterior predictions is you end up dividing out this height difference. So even though these two investigators had different values for this, they'll have the same value for the posterior predictive check because they have the same posterior. Remember, these two have the same posterior, so they'll do the same posterior predictions. So this is like, if you do the Bayesian version of this, here, you kill this one objection, kill one of my objections to this, my biggest objection. But anyway, so now we train, and that gives us, if you're a frequentist, it gives you theta hat sub k, which is the parameters you got by optimizing not including k. And then you predict in the units, in the language I used earlier, you predict for data k the model prediction at, say, the locations of the k data given the parameters that you got leaving out the k data. So you predict the k data leaving out, and then you can construct chi-squared or the likelihood, whatever you want to do it. If it's chi-squared, it would just be yk minus m xk theta k hat over sigma k squared. It would be like that. That would be like the chi-squared for the kth prediction. And then you can, and now we can cycle over all k, you see, and leave out the different k's. So we can do a sum over k of that, and look, it looks like chi-squared. You've just produced chi-squared for your whole data set, but it's a chi-squared in which you never use that data point to predict itself. Each data point was being predicted by the other data. And the nice thing about this is minimized when your model is good at predicting new data. And so that is my recommendation. And of course, I also have to say, I also recommend these more statistically clean things. But if you haven't done this, if you haven't done these splits to begin with and you want to ask predictive questions, this is a way you can ask predictive questions of your data. Yes?
So I'm confused. How is this different to blinding?
It is different from blinding because in the end, all of your data are being used. You are using all of your data, so you are cheating here. You are looking at everything, even though, so it's a bit subtle. You have to get a little adversarial to succeed here and fail here. So it has to get a little adversarial, but it can get there are weird things. Like for instance, when you look at the whole data, you might find that there's some trend in your calibration parameters that you would sort of take care of here and you wouldn't here, and really it is a problem with your model, but it's kind of hidden here. So I don't know. I don't quite have any. I don't have an adversarial example, but there are adversaries you can construct. Yeah, Viviana.
So, like in machine learning, if you have hyperparameters, you can do nested cross-validation.
Yeah.
Can you do something here to do model selection? You do model selection doing nested cross-validation?
Good. So I haven't thought about like all the ways of going up and up and up here.
Okay.
We use this, actually the main thing we use cross-validation for in my group is not literally model selection. We use it for setting hyperparameters. So it is exactly things like I mentioned in the spectrograph, where you have traces in the spectrograph. Do you fit them with a second order polynomial or third order polynomial or fourth order polynomial? It's just a qualitative choice. They all kind of work. You don't really know and you don't care. So when it's like we don't know and we don't care, this is a good way to kill those parameters. Or another thing that I get asked a lot is we'll do a mixture of Gaussians model of some density, and we've used 128 Gaussians, and people are like, why not 129? And we're like, because it's not a power of 2. And they're like, that's not a good answer. And then if we really get forced, we would go to cross-validation, where we try larger and smaller numbers of Gaussians. And one of the reasons, by the way, why does cross-validation work? Let me just say a little bit about that, because there's a beautiful it's a very beautiful thing. So imagine, and we have some demos. I didn't bring a demo, but there's some beautiful demos you can make. Actually, this is a very simple Jupyter notebook to write, which is I have a set of points here, and I want to ask whether they're better fit by a straight line or a Gaussian or a cubic or whatever. So I don't really care what functional form I'm using. I just want to use the best one. And the reason cross-validation works is that if you have a model that doesn't have enough freedom, it does not do a good job. It doesn't have enough capacity to meet the data, so it doesn't do a good job of predicting left out data. But then if you have a model that has tons of capacity, you can have a model that goes right through the data. But then when I leave out this data point, it gets very far from the model because the model isn't forced to thread through it. So cross-validation works very beautifully in situations like this. And what you end up getting is you write this cross-validation chi-squared. So you have a cross-validation chi-squared versus the order of your polynomial. 1, 2, 3, 4, dot, 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 dot. And generally what happens is your cross-validation chi-squared, oh, it goes the other way. The cross-validation chi-squared drops really dramatically at the beginning because it really just isn't fitting the data until it gets enough freedom. And then it generally rises very slowly because, in fact, a fourth order polynomial and a fifth order polynomial and a sixth are all pretty similar in this case. But then as the number of parameters starts to get large, it does a bad job again. So generally, your cross-validations look very kind of smooth, and then you know you should be operating around here.
So
that's kind of typically
cross-validation chi-squared is a thing. I can point to
Yeah.
I can Google it.
Yeah, if you look up the cross-validation like web pages, I don't know if they literally give a cross, but we just define it. We end up defining it in the paper, and we just call this thing. We give it a name. We're just very.
But I think
There's a
whatever
cross-validation
score you
likelihood in
use
general.
will work, right?
Say again?
I mean, in this case, the chi-square is just a score. You know,
It's just a
could define
score.
an evaluation method.
You're right. You could have
If you
used.
want, and it will still-
I like this score because it has a probabilistic interpretation. This is related to the logarithm of the likelihood. But Viviana's making a very good point, whereas all you really need is a score here. It could be any score, and the one with the better score is better, unless your score is dumb.
But I will also have.
Unless the score is an error.
Yeah.
That's
Unless you
it's
made a
very-
mistake.
It's very costly. I have to do optimization
Yes.
for K data.
Ah, good. There's a good question from Wolfgang. Isn't this costly? I have to do my optimization k times. Yes, but it's way less costly than doing integrals. So if you can afford to do your analysis, you can probably afford to do your analysis 4 times. And a 4-fold cross-validation is still better than nothing. So that's why we did 2-fold. I was saying, like with this project I did with Eilers, we only did 2-fold because it was expensive and we wanted to sort of be able to fully visualize and inspect it. We just went 2-fold. But if whatever. Yeah, it's not cheap, but it is way cheaper than most alternatives once your model gets complex. And then, as I said, so good, Viviana's point is very nice that it's just a score. So a different score I could have done would have been the posterior prediction for YK, right? Where I take the posterior out of this training, and then I do a marginalized prediction for M. So this would be like the average of M over the posterior for these thetas. And that would be another score you could use, and then you would be doing a fully Bayesian thing, and it would have an interpretation of Bayesianism, and it would be better than the thing I erased over here. I have a 6th point, and I have 3 minutes. Good. I want to say one last thing, which is my favorite thing in model selection. My favorite thing in model selection is 6. Nested models. So nested models, that's the idea which I mentioned at the beginning, that you might have planet data on a star and you don't know whether the star has 4 planets or 5 planets or 6 planets. Those models are all nested in the sense that a 6-planet model has 4 planets in it. And so there's no reason to separately ask about 4 planets when you're already asking about 6 planets. Now, there's a bunch of technical questions that come in about nested models which are pretty complicated. But imagine you believe that you have an infrastructure in which you can model 6-planet systems. I actually don't believe literally any of the literature in exoplanets above 4 planets. But anyway, maybe Rodrigo would disagree.
No,
but anyway, imagine you believe you can in fact estimate the posterior probability on a 6-planet system. You've got a lot of parameters there, all of the initial conditions of 6 planets and their masses, probably plus some nuisance parameters, so it's pretty nightmarish. But anyway, imagine you can do all that. Then the question of whether there are 4 planets, 5 planets, or 6 planets can just be phrased as a parameter estimation within the 6-parameter model. You can ask of the 6-parameter model, did all the planets get non-zero masses? Because if some of the planets got 0 mass, you did the 6-planet inference, you did it all, some of them got 0 mass, there's your model selection. Why additionally do model selection? The model just told you that these planets are 0 mass. That means they don't exist. Drop them, or just conclude there are only 4 massive planets in the system because we allowed there to be 6 and 2 of them got 0 masses. And the nice thing about that is you just do inference like you already know how to do, just do inference, and it actually selects the models for you. So if you have nested models, you can turn your model selection into an inference. Now this goes back, if I'm honest about it, this is back to being a likelihood method. So this is not predictive. This is a likelihood method, so we're back to being likelihood based. This is asking, does the likelihood prefer a certain number of planets? But if you can do this, it's very funny. Dustin Lang commented to me a few years ago, this is a really strange thing to say, because the fully marginalized likelihood, so imagine we're asking whether the 6th planet gets 0 mass. I'm doing a 6-planet system. Some people say there's 5 planets, some people say there's 6 planets. There's a big debate. So I do a 6-planet model and I find that the 6th planet gets 0 mass or negligible mass. So I'm like, sweet, it's a 5-planet system. Now when I say that, what am I doing? I'm going to look at the posterior on the planet mass, the 6th planet's mass. So I take my whole insanely complicated posterior, which is like 50-dimensional or 55-dimensional. I integrate it down to just the mass of the 6th planet, and here's 0, and here's something, and I find that my posterior looks like this. So I find that my posterior is saying, actually, there's really no support on this planet. Basically, this planet has no mass. And so really, there isn't a 6th planet, or there's no evidence for it in the data. That's what I conclude. The interesting thing is, to make this plot, I had to integrate out 49 of my 50 parameters. I did 49 dimensions of that fully marginalized likelihood, and I got an answer that I believe. But if you do the 50th dimension of integral, you'll get an answer which I don't believe at all. Because I just told you the fully marginalized likelihood, I don't believe that. If you fully marginalize the likelihood, I don't believe your answer at all. But if you integrate out only 49 of the dimensions, I'm like, cool, that's a great answer.
Because you get to renormalize this.
Because of the renormalization. And it has to do with the fact that if you only do 49 of the integrals, you then renormalize to get unit. And then that takes out that normalization thing. So it's a funny kind of joke that I'll let you do 49 integrals in your 50-dimensional space, but I won't let you do all 50. But This is a beautiful thing. It's very non-controversial to switch to this mode. It avoids all the philosophy and bullshit of model selection. It just comes down to a question of like, do we see an n sigma? So you'd kind of say, well, this would be a detection of the sixth planet. This is a non-detection. And of course, there's still you're still going to be left with a heuristic choice. And one thing I should have said, point 7, you're always making a heuristic choice at the end of the day. You have to decide what delta chi-squared cutoff you take, which AIC or BIC do you use, what differences of cross-validation likelihood you deem to be significant, and so on. You do have to make heuristic choices. But yeah.
It's kind of a technical question, but let's say you were doing a 6-planet model, and if you put the mass of the planet as a model parameter,
yeah,
you don't want start having negative masses, right?
Yes,
so you could either put priors that are just hard at 0, or you could say, well, maybe I should use the log of the mass or something.
Yeah.
In that case, if you use the log of the mass, you will always have some,
You'll never hit 0.
Right. So, you said 0 or negligible. You kind of threw that in there.
Exactly. I was being a little loose. Whenever you do this, you take on some kind of heuristic threshold, meaning there's going to be some point at which you say, and like if you're a particle physicist, you would take the mean and the variance of this and ask whether it's 5, whether you have to go 5 variances over to hit 0. That would be how a particle physicist would do it. But you have to make a call here about what statistic do you do on this diagram. And as you say, probably if you're using realistic priors, this actually does that because you cut off 0 because you're working the log of the mass. So yeah, you do have to make decisions there, and it's not totally trivial. But I have to say, if you follow back through the things I said earlier, almost all the methods I've said involve some heuristic threshold. But you might say, well, we'll do cross-validation, and I'll just choose the one with better cross-validation score. But that isn't quite true, because if they're very similar in cross-validation score, and one takes 100 times longer to compute than the other, you're going to go with the, you still in your mind actually do have heuristic thresholds and cutoffs through this whole thing. So here is a case, but here it's very explicit. You'd have to make an explicit cutoff. And a good example here, by the way, is co-moving stars. So Sung-Young Oh and Adrian Price-Whaley and I looked for stars in Gaia that are co-moving, and we did it as a hypothesis test. Either they're co-moving or they're not, and we made 2 models. But then after we did it all, we realized the 2 models are nested, and we could have just estimated the velocity difference between the 2 stars, and all of the math would have been easier in that project. So we kind of made a mistake by not realizing that. Daniel.
So for these heuristics,
Sorry, I just called him Daniel.
Really, we have to make our choices for all these heuristics before doing any of our analysis, right?
In principle, yes. In practice, obviously, you only realize you have choices after you've started doing your analysis. But in principle, this is one of the reasons it's a good idea to think about your data analysis before you do it, because you'll anticipate that you're going to hit a point where you're going to have to, it's good to like predict what plots are going to look like, and then you realize, oh shit, we need to pick a threshold. So in principle, you should do it in advance. In practice, the world is often messy. You might get a posterior on this that looks like this, and then you're like, is that a detection or not? So in reality, the world might leave you with something where you have to read aside. And then you can write in the paper. If you want to be really principled, you write in the paper. In advance, we decided to use this mean and variance thing, but it didn't occur to us that the posterior would look like that. Since the posterior looks like that, the situation is more complicated. So I think it's important not to be too principled. The really principled thing is to make a prediction. So in this model, you can say the planet, this model and this model make qualitatively different predictions for the future, and if you measure the radial velocity of this star at this date, you should see this in this model and that in that model, and that's really where you want to be more. It's easier to be principled when you think about the future than when you think about your current data. And cross-validation is kind of a way to pretend you were being principled when it's too late. But really, our problems when we write papers is not to be principled. Our problems when we write papers is to make predictions. I think that's better thing. Yeah.
Last thing. So in this case, can't you use the evidence again, since your priors now are the same? Then you don't know that.
Right, one of the things that's interesting, Vivian asked about the evidence in this context. Actually, in nested models, the evidence makes more sense. So the evidence is a less stupid thing to do in a nested model. So nested models are actually good for a number of reasons. Because in the nested model, all the other parameters can be identical. And so, right, so if you compare 5 planets and 6, you can ensure that in the 5-planet subpart of the model, all the priors are identical. And that, I think, that is important, and that does make it better. So this nested case, whenever you're in the nested case, you should step back and think, oh, we're in the nested case, what things do we get for that? And one of them is that. And you should really pin your priors in the correct ways, yeah. John?
Well, it seems like you could also run into problems here because you could have covariant masses between two planets. So you don't get 0, instead you just get a trade-off in which one is correct, and maybe if you toss the other one, you get a
Good. John's saying that this, but I'm going to retranslate what John's saying to that this projection of the posterior can be very misleading. Because it might be that this posterior is far from 0, but only when some other mass gets driven to 0 or something. Or it might be that this is only close to 0 when some other mass is large in such a way that really there must be some other mass there. So you really want to look at as many projections of your posterior as you can. Of course, if you're in 50 dimensions, you can never look at all your projections. You might think, oh, I can look at the 50 by 50 corner plot. That is a very tiny fraction of the projections you can look at. And so there is also a question of like, there's many reasons you should try to avoid being in a place where you have 50 free parameters. But if you have to be there, you really need to do a lot of work to understand what you're doing. Yeah, this is really a blunt tool. We're adjourned.